Imagine you're part of a team of 100 developers, all working on a single online shopping system. But there's a catch. Everyone has to write their code inside one single file. Within days, shoppingsystem.c hits 50,000 lines. Developer A's login update and Developer B's payment edit hit the same line, a collision course. This lack of structure shatters progress. A login bug breaks checkout, and finding the crash in this giant file becomes impossible. Treating software as one giant interconnected block makes it difficult to maintain, impossible to test, and slow to develop. Instead, we can look at the design of a smartphone. The camera, the speaker, and the battery are all distinct parts. If the speaker breaks, you don't have to redesign the entire phone to fix it. This is modular design. We divide an application like WhatsApp into independent parts. Each module handles specific tasks in isolation. Multiple developers can work simultaneously, testing the payment module without touching the rest of the code, or reusing login logic for an entirely different app. But simply splitting code into different files isn't the whole story. To ensure the design actually works, we have to look at the relationship between these parts using two specific metrics. The first metric is cohesion. This measures the relationship between everything happening inside a single module. In this login module, we see functions for checking usernames, passwords, and generating codes. Because every line of code serves the exact same goal, the module is efficient and easy to understand. It's staying focused. Think of a bowling coach. If they stick to teaching swing, spin, and yorkers, the training is effective. But if they suddenly start teaching you how to cook or drive a car, the focus is gone. The same thing happens in a module. If your login code also tries to play music or calculate payroll, the internal logic breaks apart. This is low cohesion, and it makes the module confusing and difficult to modify. High cohesion ensures that every module has one clear purpose, making it easier for developers to find what they need and fix bugs without hunting through unrelated logic. While cohesion looks inside, our second metric, coupling, looks at the connections between different modules. Imagine roommates who share everything: their wallets, their clothes, and their phones. If one roommate loses their wallet, everyone is suddenly unable to buy groceries. They're too dependent on each other. In software, this is high coupling. When modules are tangled together, changing the way a user logs in ripples through everything, breaking the payment and inventory systems. It makes the software fragile. We aim for low coupling instead. Here, modules work independently and only interact when strictly necessary. Updating the login code might require a small check from the order module, but the payment system remains completely unaffected by the change. Take a moment to think about this. If a payment module only contains functions for processing credit cards and verifying balances, is that an example of high or low cohesion? That would be high cohesion, because everything inside the module is focused on one task. Balancing that internal focus with external independence is how we build complex systems that don't break under their own weight. When we combine these concepts, we get a clear target for software architecture. We want modules that are tightly focused on the inside with minimal dependencies on the outside. This approach ensures the system is reliable. Because each part is independent, a failure in the notification module won't crash the entire database, keeping the software stable for the user. To summarize, cohesion happens inside the module, where high is the goal. Coupling happens between the modules, where low is the goal. This relationship is the foundation of professional software design. It's what allows a small team to build an application that eventually scales to millions of users. Now that we've designed a modular, cohesive system, the next challenge is ensuring it actually works. In Part 20, we'll move into software testing, how engineers deliberately try to break their own code before a user ever sees it. Understanding the balance between cohesion and coupling provides the structural framework necessary to manage the complexity of any modern software project.